Good morning, everyone. This is M. Ashwin from CSC Regular, rule number 24011A0526. Today, I am going to give a presentation on topic on analysis of series and parallel RC circuits. Let's go to the topic. Yeah, in this slide, we can see the series RC circuits. So, in series RC circuit, both the resistor and capacitor are in series, so that the current will be same in both the resistor and capacitor. But the voltage will be different, but the source voltage must be equal to the sum of the voltages in resistor and capacitor, and their values will depend on their impedance, and their total impedance in the circuit is the sum of the resistance and the reactance of the capacitor. As I said that in series RC circuit, voltage will be different in both resistor and capacitor. So they will depend on their impedance, and the current will be same in both of them. As we can see here that some relations. For resistor, we know that from Ohm's law, V is equal to IR. From that, we can get that R equal to V by I. So there is a capacitor. We know that the capacitor resists the sudden change in voltage. So for time dependent voltage, the current will also changes. So as the voltage changes, current will also changes. So for that, the relations are given here. So we can also find the energy for the resistor by integrating from given limits by taking I and V values. For capacitor, we know that Q equals to CV. So from that, we get that C equals to Q by V. So as the current is changing, we can find the voltage by integrating in the given time intervals. So for capacitor, the power energy is given by W equals to 1 by 2 CV square, and the voltage is changing with respect to time. So we have to find the voltage at that given time. In this slide, we can see time response of series RC circuits. As the time changes, voltage across the capacitor changes as it charges and discharges. For charging of capacitor, voltage is given by V of t equals to V naught into 1 minus E4 minus t by tau, where V of t is the voltage at that time and V naught is the maximum voltage, and tau is the time constant, where tau equals to RC, where R is resistance and C is capacitance. And for discharging, it is given by V of t equals to V naught into e power minus t by tau. Same terminology will be used for this also. So at right, we can see that V equals to IR plus VC, which is nothing but total voltage equals to voltage across resistance plus capacitance. So here we can find the relation that I equals to C into dV by dt. So by substituting the value of I in the equation 1, we get that V equals to RC into dV by dt plus VC. So we can find that this is a first order equation. By integrating it, we can find the equation for charging and discharging. So now coming to parallel RC circuits, in this both the resistor and capacitor connected in parallel, so that voltage will be equal in resistor and capacitor, but the current will be different in both resistor and current, but the total current must should be equal to the sum of the resistor and current. As we can see here, impedance for that formula is given by 1 by Z equals to 1 by R plus 1 by Xe, which is same as that of when both are two resistors are connected in parallel. So same formula will be used here, but instead of one more resistor, we have two capacitors. So we are taking Xc, which is 1 by omega C. So in parallel RC circuit, voltage will be equal in both resistor and capacitor. So in this slide, we can find the current relationships in parallel RC circuit. We can easily find the current to the resistor using Ohm's law, that is I equals to V by R. But for finding the current to the capacitor, it is given by I equals to C into dV by dt. So we know that voltage will change with respect to time. So we have to differentiate and we have to find the value. So sum of currents through both of these must be equals to the source current, that is I total must be should be equals to IR plus IC. So in the right side we can find a circuit. In the circuit we can find that both R2 and R3 are in parallel. So the voltages across them are equal, that is V2 equals to V3, and using Kirchhoff's current law we can say that I equals to I2 plus I3. Same as that in series RC circuits, in parallel RC circuits also, voltage is changing with respect to time. So their equations are same as that of parallel, but the values depends on the presence of resistance and the time constant, that is tau, that is which is equals to RC. will be constant at all time. In this slide, we can see about frequency response of RC circuits. As the frequency changes, the responses, which is nothing but the values of RC changes. So the behavior of RC circuits is also known as frequency dependent behavior, which affects their performance in AC applications. As we can here find a term called as cutoff frequency. This is the frequency at which the output voltage will be equal to the 70.7% of the input, and which is determined by the RC values. And by analyzing the frequency responses, engineers are used to design filters. So by using the filters, we can get the desired frequencies from the given input voltages. So in this ways, we have applications of RC circuits. Here is one more application of RC circuits. So these are used widely in timing circuits such as oscillators and timers, and these are also used as filters in audio and radio frequencies to eliminate unwanted signals and to get the desired signals. So understanding RC circuit behavior is essential for our day-to-day life for applications of signal processing and control systems. Here is a summary of RC circuits. Series and parallel RC circuits exhibit distinct behaviors that are essential for their application. So by studying about series and parallel RC circuits, we can find their applications in such ways like signal tuning, etc. Time constants and frequency responses are critical for analyzing and designing effective circuits. As I said that studying of RC circuits is crucial. So by making masters in RC circuit analysis, it becomes a foundation skill for electrical engineers and technicians. I'm thanking Raju sir for giving me this opportunity, and that's it. Thank you.